this gives us the rules we needed to draw image formed by a concave mirror. And so let's take a systematic look at how to form an image. Image formed by concave mirror. Okay, two rules. One is parallel beams. Okay, if a beam is parallel to the optical axis, you know it's going to hit, after getting reflected, it's going to hit what? The focal point, right? The second rule is the optical center. What about the optical center? Any beam that passes through the optical center after getting reflected, where is it going to go? Yeah, it's going to go right back, bounce right back. It doesn't go sideways. Okay, with that in mind, let us now draw the image formed by any object in front of a concave mirror. Okay, it turns out it really matters where you put that object. Okay, how far you put that object in front of the mirror. Here, let's look at several cases. Okay, let's look at several cases. Case number one, I have an object here. Okay, I have an object here that is a distance from here to there that is greater than the radius. Okay, now remember, from here to there is one f, that's f is half of r, that's the focal point, and from here to there is another f, right? So here, this distance between the object and the image and the mirror is greater than 2f, greater than 2f. 2f is from here to there. Okay, the distance between the object and the mirror is called the object distance, denoted as p in our textbook. So in other words, p is greater than 2f. Forget about that. Okay, that is not where the image should be. Let me erase. Okay, so we erase that guy, and then here is our object. I want to know where the image is. Okay, in fact, all you need really is to find where the head and the tail of that object is, right? And as far as the tail is concerned, you know the tail is going to be, the image of the tail is going to be somewhere on that line, because if you think of a line coming from here along the optical axis, it's going to bounce right back, right? So you know it's going to be somewhere on the optical axis. All we have to do is look at the head. The head is right here. This is the object right here. I want to know where the image is. And again, the way I do that is imagine there are a whole bunch of light beams coming out. And let me select two representative light beams coming from that, getting reflected by the mirror wherever they converge, and that should be where the image of that head is. Okay, so two rules. Rule number one, what? A parallel beam, right? Parallel to what? Parallel to the optical axis connecting C and F. So let me draw that. Okay, so here is a beam that is parallel to the optical axis. Where is it going to go? Well, remember the focal point? Okay, so it's going to pass through the focal point. It's going to do this. Okay, it's going to do this, so it goes this way. Okay, it goes this way. That's one. Okay, now, the second beam. Another beam coming from the same object. Okay, we can do one of the two things. We can aim at the focal point. It's going to go this way. Or we can aim at the optical center. Okay, suppose I aim at the optical center. Where is it going to go? If I aim at the optical center, after hitting the mirror, it's going to get reflect right back, right? Comes in and comes out. So now you got two beams after reflection, one going this way, one going that way. Where do they converge? They obviously converge here. Okay, this therefore is the image point of the head of the object. And the tail of the object must be there, and therefore I can then draw the whole image. The whole image is like this. Obviously it's upside down. Okay, now is it real or is it virtual? Well, look, you could actually light rays, one this way, one that way. They actually pass through that point. They cross that, real light rays actually cross that point, right? If you put a screen here, the screen will be illuminated with an upside down cross. So this is a real image. Okay, so it's a real image. Let me write down the properties. It's real. It's upside down, or we say inverted, right? Inverted. What else? Is it bigger or smaller than the actual object? Well, it is smaller. In other words, it is not magnified, rather it is minified. Okay, minified. this image is real, inverted, and minified. And that is when P is greater than 2f. Again, P is the distance between the object and the mirror. Alright, now let's bring the object closer and closer. This time I'm going to move that object beyond one focal length, two focal lengths. So it's closer than two focal lengths. We move it beyond the optical center, between C and F. Okay, between these 2 points, C and F. I want to know where the object is, where the image is. You know, I have these rules that I can apply. I don't really have to memorize anything by, memorize the properties of the image just by brute force. All I have to do really is to draw the ray diagram. So here is another drawing. I start from the tip of the object and I draw a line that is parallel to the optical axis. We all know where that line is going to get reflected, right? It passes through the optical center. Pass through the optical center, it goes like this. That's one. Okay. Another one? Well, you can draw a line like that. So it passes through the optical center. It's going to bounce back like that. This is the focal point. But you can also, probably easy to do it this way. You just aim at the focal point. You see? You aim at the focal point. Okay. Where's it going to go? Well, if it passed through the focal point, after reflection must be parallel to the optical axis. So this is where the beam is going to get reflected. Okay, so this time we have two beams after reflection. One going this way, one going that way. They converge where? They converge at this point, right? They converge at this point, and therefore the image of this object would be like this. Okay, you see, just like that case, this is the real image because light rays actually converge at that point. It is a real image. It's inverted just like that. But this time, the image is actually bigger than the object itself. So it is magnified, okay, not minified. So you see, as I bring an object from very far away, gradually, I always get a real image upside down, but gradually as it brings closer and closer and closer, I find that the image gets bigger and bigger and bigger as it goes backwards. Okay, now, one last case. Suppose I bring this object even further in, so that it is now within one focal length of the mirror. So it's here, see, within one focal length. Again, I can draw two typical light rays to represent the light rays coming out of the tip of the object, so I know where the image is. One light ray, right, parallel to the optical axis. So you tell me, where does it pass through now? Well, you're veterans. You know that it must pass through the focal point. The focal point like this, right? So here's one light beam, pass through the focal point. Okay, now you can draw another light beam. How do you draw it? Well, how about this? How about if I draw a light beam like this? A light beam like this. This beam goes from here to there. And if you extend it backwards, it appears to originate from the optical center. Now, of course, the light beam can only go forward, it doesn't really go backwards. But this light beam has the same direction as another beam which passes through the optical center. So you know, after reflection, it's going to bounce right back, right? Because this is 90 degrees. Okay, so it's going to bounce right back. Now, take a good look at what happens now. You get a beam coming back like this. You get another beam coming like that. You see, so if you put your eye here, what are you going to see? You see one beam going this way, one beam going that way, right? Obviously, they are getting further and further apart, these two beams. They will never converge on this side. When they do not converge, you are not going to get a real image. Okay? On the other hand, these two beams appear to originate both from the same point somewhere behind the mirror. Okay, now let me ask you, is there really something behind the mirror? No, it's totally dark. No light rays can penetrate the mirror. It's just a reflection, not refraction. Okay, but yet these two beams appear to be from there. So therefore, when you look at it, what do you see? You will see a virtual image, okay? You're going to see a virtual image. Let me extend it backwards. There's broken lines. You're going to see a virtual image of the arrow, the tip of the arrow, the image of the tip of the arrow is right there, and I'm going to use broken lines like this. Okay, it is behind the mirror, which no light can penetrate, so therefore it is obviously not real light rays. It's virtual. Okay, so it's virtual, right? It's not inverted though. It's right side up or upright, right? And it is also bigger than the object itself. It's magnified. This is when you bring it within one focal length. Okay, so you can think of some application of this setup, by the way. You have a mirror, okay? Now you have, in order to see this effect, you gotta put an object within one focal length. Okay, you can achieve that by making this mirror almost flat. It's spherical, but it's almost flat, which means the radius, the optical center is way back. It's very, very long. Okay, the radius is very, very long. So it's a slightly curved concave mirror. It's almost flat, but slightly curved. And so this radius is very long, so we can use it to see our face, for example. And since the optical center is way back, our face is right here, we are going to get into this situation, right? And what you see is the image of our face. It's right side up, which is what we want. We don't want it upside down. And what's the nice thing? It is bigger than the real face. Okay, so we can use it as a magnifier. So, what we have learned is that a spherical concave mirror is able to produce images of various kinds, from real to virtual, from upside down to right side up, from minified to magnified, depending on where you put the object. This is more versatile than just a plain mirror. As a matter of fact, you can think of a plain mirror as a special case of a spherical mirror, with the radius of curvature equal to what? Equal to infinity, of course. Okay, so because radius curvature is infinity, no matter where you put yourself in front of that plane mirror, it's always going to be the distance between you, the object, and the mirror is always going to be less than the focal length, because the focal length is infinity, right? So you're always going to look at only the last situation. This situation, you're going to see a virtual image right side up. Okay. You can see why we're interested in spherical mirrors, because we can use it to produce different types of images depending on what we want. Now, the way we located the image is by drawing. This is a very important technique. It's called drawing ray diagrams, okay? Ray diagrams. Again, all you need to do really is just draw two representative points. See where they converge? That is where the image is. Okay, but another very good important way to locate the image is by calculation, and that is, suppose I know the distance between the object and the mirror. We call it P. We also know the focal length F between here and there. Between knowing P and F, is it possible for me to locate the image by just calculating the distance between the image and the mirror? In other words, can I find Q between here and there? It turns out you can do that. There is an equation relating P, Q, and F. Okay, that is called the mirror equation. And let's see how that works. The so-called mirror equation. Again, I have an object here of height h. Okay, height h. One line coming from the tip of the object parallel to the optical axis. It passes through the focal point that you can see here. Okay, another line aimed at the optical center bounces right back. So they cross each other. Two reflected beams cross each other at this point. This is where the image is formed. You get an upside down object image at this particular case. In this particular case, you get an upside down image of height h prime. Okay, it's real. And by definition, the distance between object and the focal and the mirror is P. This is P. The distance between the object, the image, and the mirror is Q. So between here and there, it's Q. Okay, between here and there is Q. I want to find a relation between P and Q, given the focal length between here and there, which we call F. Okay, F. Now what we're going to do is we're going to ignore this little distance. How can we do that? Because remember, we want only near axis beam, so this h is far less than what? Than the radius r. Okay, so the way I draw it, h and R, this is R. They're not that different from one another. What I should have drawn is a beam coming in like this, right? That's really near axis, but that's kind of hard to see. Okay, but if you imagine if you actually draw something like that, then you're looking at a very, very small portion of the surface, of the spherical surface near the vertex, and therefore this distance is pretty much 0, okay? So, you know, we can say this is the, pretty much this point is the vertex. Okay, question. How does one find Q in terms of P and F? Okay. In fact, we can easily do so by looking at some simple geometry. After all, this is geometric optics, right? Now, take a look at these two triangles. I have this triangle and I have that triangle. Obviously, they are similar, okay? So they are proportionality I can think of. What's the distance between here and there? Well, remember, the whole distance between here and there is the image distance Q, right? So this is F, so this must be what? Q minus F. Q minus F. You got Q minus F, and you got F. Okay, so if you compare these two triangles, you have H prime over H equals to, okay, H prime over H equals Q minus F divided by F. Q minus F divided by F. Remember that? Makes sense? This over that equals this over that. Right? But that is not all. I also need P somewhere in the equation. Okay? So can you think of a triangle with P in it? Well, they may not be a whole triangle which contains the entire length. It's too long. But what you can do is you can look at this triangle. Okay, this triangle has one side length H, and it's got that side length from O to C. How much is that? Well, between O and V, that is P, and then from here to there, that's R. That's the radius, or 2F, right? So between O and C, what's that length? The length between O and C is pretty much P minus what? Radius R, which is 2F. Right? Now, this triangle is also similar with that triangle. And how far is the distance between here and there? Well, look. Between here and there, that is between the optical center and the focal point, and that is 1F, right? There's 1F, just like from here there is also 1F. So 1F between here and there. So what is the distance between here and there? It's 1F minus this number, Q minus F, right? So it's F minus Q minus F. What is that? 2F minus Q, right? Okay, so let's take a look at this triangle versus that triangle. I have H over H prime. Actually, H prime over H equals to this over that. In other words, 2F minus Q divided by P minus 2F. Right? So you see, I have established two expressions for H prime over H. One is from these two triangles, the other is from those two triangles. Of course, they must be equal to each other, so I have Q minus F over F equals 2F minus Q divided by P minus 2F. Let's cross multiply, okay, and just see what we get. Okay, let's see what we get. Q minus F P minus 2F equals F times 2F minus Q. Okay, work out some algebra, shall we? PQ minus 2QF minus FP plus 2F squared equals to the right hand side 2F squared minus FQ. Am I right? Okay, now cross out some common terms. There's 2F squared, there's 2F squared, there's negative P. Okay, hold on. There's FQ, there's FP. Okay, there is a 2QF, there's 1QF, and therefore I can cross that 2 and I cross that term. Okay, so now we have only 3 terms left. This is gone, this is gone, this is gone. Only 3 terms left. PQ minus QF minus FP. That equals 0. Right? Okay, let me divide everything by PQF. Okay, divide everything, every term, by PQF. So you divide this by PQF, what do you get? You get 1 over F. Minus divide this by PQF. Q is gone, F is gone, P is left. The last one, minus what? P divided by PQF. So F is gone, P is gone, Q is the only thing that's left. So you find that 1 over P, 1 over F minus 1 over P minus 1 over Q equals 0. And let me move these P and Q to the other side. I get the famous mirror equation, which I'm going to put right here. 1 over F equals 1 over P plus 1 over Q. Okay? Very simple and elegant. Now, does the result from the mirror equation agree with our plotting, with our ray diagram? Of course they should. Okay. One of the things that we notice is the so-called magnification. Okay, magnification. That is h prime over h. H prime over h. Well, from here we see h prime over h is q minus f divided by f. I can rewrite this expression a little bit to make it easier to see. If I know q and p, okay, if I know q and p, can I find the ratio of h prime over h? Okay, it turns out you can easily do that. Imagine I have an object here, okay? This time I produce a beam of light coming from the head of the object aimed at the vertex. It's going to reflect that way, making these two angles the same, because after all, this optical axis is now the normal, okay, at that point. So these two angles are the same. So look at these two triangles, right angle triangles. They're obviously similar triangles because they have the same angle theta here. This distance is P, and that distance is Q. So obviously, h prime over h can also be written as Q over P. H prime over h tells you how large the image is in comparison with the object. If h prime over h is greater than 1, magnitude-wise, we say it's a magnified image. If it's less than 1, it's a minified image. So to magnify the image, all you need is to have a q value greater than p, or if it's q less than p numerically, then you get a minified image. Okay, now does that agree with our drawing? Now, take a look at our drawing. In our drawing here, we know the image is smaller here than the actual object if p is greater than 2f. Alright, p is greater than 2f. Now, think about it. 1 over p plus 1 over q equals 1 over f. Alright? And if p and q are equal to each other, if they're equal to each other, then how much would each be equal to? Well, 1 over p plus 1 over p is equal to 1 over f. So if p and q are equal, they both must be equal to 2f. See that? Because 1 over 2f plus 1 over 2 equals 1 over f, right? So if the object is placed exactly at the optical center, that is p equals 2f, then p and q will be equal, and look at this h prime over h. The object would have the exact same size as the image. Okay. On the other hand, if you move the object further away from C, so p is now greater than 2f. If p is greater than 2f, then q must be less than 2f. So this is the case when q less than 2f, p greater than 2f, q is less than p, you're going to have a minified image. Okay, in this case, the object is placed within 2f, okay, between 1f and 2f, and therefore p is less than 2f, and therefore q must be greater than 2f. You see here? So q is greater than p, you have a magnified image. Okay? And in particular, as I said, when p and q are equal to each other, they must be both equal to 2f, and that's exactly what we get when we draw a diagram. We draw a ray diagram while placing an object exactly at the optical center. So we put an object right here at the optical center. This is P. According to our formula, Q will be right here. In other words, the object should be right here, upside down. Same size, same location, except it's upside down. Let's see if that's the case. Okay. Here. That's one line. Another line can again aim at the focal point. Where is it going to go? It's going to go that way. Okay, see, if you draw it more carefully, you clearly will find, this by symmetry, And in this case, P and Q are equal to each other, both equal to 2f, and the ratio of h prime over m over h, which is the magnification, exactly equals 1. Okay, so the ray diagram and the mirror equation will give you exactly the same result. And you can also look at the third case, the virtual case. Okay, now remember, 1 over p plus 1 over q equals 1 over f. We can solve for 1 over q. 1 over q equals 1 over f minus 1 over p. If p is less than f, which is the case for a virtual image, okay, then 1 over p must be greater than 1 over q. I'm sorry. Again, p is less than f, right? So 1 over p is greater than 1 over f. In other words, 1 over f minus 1 over p is it positive or negative? It's negative. Okay, so q itself is now negative. You can see now, what does a negative q mean? A negative q means the image is on the wrong side of the mirror. Okay, everything is supposed to happen here. This is where light beams can reach. Behind the mirror, nothing is supposed to be there. But if an object lands somewhere there, it's the wrong side of the mirror. And what's the consequence? The consequence is that you're going to get a virtual image. Okay, a virtual image. So suppose you get a q equal to negative 3 centimeters. You know what that means? It means the object is behind the mirror by a distance of, the image